one insight that will actually pay some dividends is just to notice that all of our row operations are reversible. So to check this, let's just go one by one. So for row swapping, right, if we interchange row I with row j, how can we undo that? Well, to undo that, just swap them back, right? That's another row operation. So by doing this, we can undo this row swap operation by doing another row swap operation. All right, what about multiplying a row by a constant? What if we say multiply row I by a constant c? How can we undo that? Well, we could multiply row I by 1 over c. Right? Doing one of these and then the next will undo our multiplication by c. It is important to realize that the only reason that this is possible is because c is not equal to 0, right? We allow ourselves to multiply any row by any constant except 0. So the fact that c isn't 0 is what keeps this operation reversible. All right, the last variety of row operations is adding a multiple of a row to another row. So we could take row I and multiply c times row j. So how could we undo this with a row operation? Well, we could take row I, and then instead of adding c times row j, we could subtract c times row j. So if we started with row I and then we did both of these operations, right, adding c times row j and then subtracting c times row j, we get back to where we started because these just undo each other. All right, so all of these row operations, we can undo them with other row operations. And that turns out to be kind of a key thing. All right, with that in mind, we've seen that if we can turn one matrix into another using row operations, those matrices, if we treat them as augmented matrices, they represent systems of equations that have the same collection of solutions. And for that reason, if we can turn one matrix into another using row operations, those matrices, they're kind of related. They aren't equal to each other, but there's a certain sense in which they're, I don't know, equivalent. And for that reason, we're going to make this definition. So we'll call two matrices row equivalent if we can turn one into the other with row operations. So to make sure we understand what this definition means, let's just check if which of these four matrices are row equivalent. Well, one thing to notice is row operations can never change the size of a matrix, right? No row operations change the number of rows or the number of columns of a matrix. So it only makes sense to ask about row equivalency if the matrices have the same size. Matrices that don't have the same size will never be row equivalent. So it only makes sense to ask this question if these matrices have the same size, and they do. They're all 2 by 2. So in general, this seems like a very difficult question to answer because, first of all, there would be lots of combinations to check. We would have to check, are these two equivalent, are these two equivalent, are these two equivalent, and then these two, and then those two, and then these two, right? So lots of different possibilities to check, which seems like a lot of work. And the other problem with sort of a direct approach to attacking this kind of question is, if we can turn one matrix into another with row operations, we can demonstrate that just by writing down the appropriate row operations. But it's much harder to prove in a direct way that you cannot turn one matrix into another just with row operations. Right? It's possible that, if you try a lot to turn one matrix into another with row operations and you can't do it, well, maybe that's because they aren't row equivalent, but maybe that means you just haven't found the right combination of row operations yet. So although it's maybe not too difficult to be able to answer this question yes for certain matrices, it's actually very tricky to answer these questions no. But we have a trick up our sleeves. And the trick up our sleeves is that every matrix has a unique reduced row echelon form. So if we have a matrix, we can do row operations to get to its reduced row echelon form, right? If we had another matrix and we want to know, are these two matrices row equivalent? Well, we could reduce B to its reduced row echelon form. Okay, well, there are two possibilities now. If these two reduced row echelon forms are actually exactly the same matrix, then we can get from A to B by doing row operations, because first we do all the row operations to reduce A, and then we undo all of the row operations that would have turned B into its reduced row echelon form. Right? So here we're using the fact that row operations are all undoable using other row operations. So if these two matrices have the same reduced row echelon form, then they're actually row equivalent. Well, the other possibility is that these two reduced row echelon forms aren't the same. And if these two reduced row echelon forms aren't the same, well, we know that that means these two matrices, if we interpret them as augmented matrices that represent linear systems of equations, if their reduced row echelon forms are different, that means these represent systems that have different solution sets. And if they have different solution sets, we know that it is going to be completely impossible to turn one into the other using row operations, because row operations do not change the solution set, and so it won't be possible to turn A into B because they have different solution sets. So what we're seeing here is that being row equivalent is actually the same thing as having the same reduced row echelon form. And that's a much easier thing to check, right? Rather than checking all of these different combinations of are these two row equivalent, are those two row equivalent, we can just reduce each of these to their reduced row echelon form, and the matrices that are row equivalent will have the same reduced row echelon forms. So let's quickly do that. Let's see, for this one, I guess we need to take row 2 and add 2 times row 1, and that's going to give us 1 minus 2, 0, 1. And then take row 1 and add 2 times row 2, and that's going to give us 1, 0, 0, 1. Okay, for this one, why don't we... I see that if we just add... Well, I don't know. There are lots of ways to do it. I'm going to do the way that has the fewest number of row operations. So let's do row 2, subtract 1/2 of row 1. So the fraction arithmetic here is a little annoying, but it does turn out to zero out the bottom row. And then remember, we need to go to reduced row echelon form. So now let's take row 1 and multiply it by minus 1 over 4. So that's going to give us 1 minus 1/2, 0, 0. Okay. Notice that that's actually exactly the same as this fourth one. So this fourth one is already in reduced row echelon form, so we won't have to do anything else there. For this third one, let's see, maybe I guess we could multiply the first row by 2, multiply the second row by 3. It's not totally necessary to do this, but it makes the arithmetic a little easier. So this gives us minus 6, 4, and minus 6, 3. Then we can take row 2 and subtract row 1. That's going to give us minus 6, 4, 0, and let's see, this minus that, minus 1. Okay, now I can do row 1 plus 4 times row 2, so minus 6, 0, 0, minus 1. And then finally we can do row 1 times minus 1 over 6 and row 2 times minus 1. I think that'll do it. So then we get 1, 1. Okay, so now that we have the reduced row echelon form for all of these matrices, row equivalent matrices will have the same reduced row echelon form. So, well, there's this one and this one. So these are row equivalent. And there is these two. These have the same reduced row echelon form. So that's these two. These are row equivalent. Okay. you can see that answering this question would have been way more work if we had tried the direct method. So knowing both that row operations are all reversible with other row operations and that the reduced row echelon form of a matrix is unique gives us a great way to approach figuring out if matrices are row equivalent. So another thing, something that we should notice about this row equivalent definition that we've made is that it's what's called an equivalence relationship. And an equivalence relationship is just a relationship that has three properties. So I'm going to express this all in terms of this row equivalence relationship, but it could be any other relationship. So our row equivalence relationship is an equivalence relationship because, first of all, every matrix is row equivalent to itself. That's kind of obvious. That's what's called reflexivity of the relationship. Also, if we have two matrices A and B, then if A is row equivalent to B, then B is also row equivalent to A. That's what's called symmetry. And this one is true. We know that this one is true for our row equivalence definition because we know row operations are all reversible. And then lastly, if A is row equivalent to B and B is row equivalent to C, then A is row equivalent to C. That's called transitivity. And this is true for row equivalence because, remember, saying A is row equivalent to B just means that there are row operations we can do to get from A to B. And then if B is row equivalent to C, again, that means there are row operations that get us from B to C. And then we can just do all of these row operations one after the other, and we'll get all the way from A to C. So row equivalence is also transitive. So the reason that equivalence relationships, so relationships that have reflexivity, symmetry, and transitivity, the reason that they're important is they break up everything into a collection of equivalence classes. So, right, we have, if this is the collection of all matrices, right, some matrices are row equivalent to each other. For example, the matrix 1, 0, 0, 1 is row equivalent to the matrix, say, 1, 1, 0, 0. Right? So these sort of live in the same part of the collection of all matrices. Over here, in a different equivalence class, is this matrix. It turns out, right, these aren't row equivalent because you can't turn one into the other using row operations because they have different reduced row echelon forms. Okay, so if in this space of all of the all matrices, if you divide them up into subsets of matrices that are row equivalent, so each portion of this big bubble here represents a collection of matrices that are row equivalent. Each one of these things is called an equivalence class. I guess I don't need to write it again. Right, this is an equivalence. So each one of these is an equivalence class. And these three properties for equivalence relationships, reflexivity, symmetry, and transitivity, make it so that the collection of equivalence classes, first of all, they don't overlap. So no overlap here. And also, they cover all matrices. Sometimes you'll hear this stated as they're mutually exclusive, they don't have no overlap, and mutually exhaustive. So they cover all matrices. And that's a really nice property for a relationship to have because it lets us think of instead of thinking of all matrices, it lets us think about the matrices sort of at a chunk at a time, right? We can think about just each individual equivalence class because every matrix in an equivalence class sort of has similar properties. The similar properties here really means the same. It represents a linear system that has the same collection of solutions. And what we'll see is that is an especially nice way to think about matrices for certain kinds of questions about matrices.